We're talking about metric spaces, which really is one of my favorite topics of this semester, and I hope you all end up enjoying it. In a lot of ways, metric spaces was one of the places where I first came to really, a lot of the ideas of analysis and then calculus and the epsilons and deltas all kind of really started to congeal and make sense to me when I started studying metric spaces. Metric spaces are treated differently in a lot of different books, and there's really two main camps. One camp is that we should introduce metric spaces early in the semester. They should be one of the first topics of the semester, and then everything in this semester is told through the lens of a metric space. Another is what our book does and what I've decided to do, and that is we do all of the problems and all of the concepts of analysis in terms of real numbers, which make the most sense to us, and then we define metric spaces and go back and capture and go back and rethink what should these ideas look like once we've defined a metric space. So in a sense, what a metric space is really trying to do is they're trying to capture this idea of distance. And so we'll always have a metric space, we'll always have a space x, and then we'll always have some way of measuring distance. So let's get to the definition. So a metric space consists of a set X and a function which this book likes to use rho. Some other books use d. There's actually I've seen deltas. There's lots of different things that people use for a function. A function, and they're going to use this notation, x cross x to the real numbers. What does that mean? Well, it means rho is made up of two numbers, x and y, and these are both two elements of whatever our set is, and then the output is some number d, which is a real number. So your set doesn't have to be made of real numbers. Your set could be made of vectors. It could be made of any sort of objects, functions. We'll talk about all sorts of different functions. This function is called the metric. So rho is the metric. And a metric has to have three properties. So a metric has three properties to be considered a metric space. So the first property is that rho of xy needs to always be positive. So remember, we're kind of trying to generalize the idea of distance. And so the important thing is that rho of xy is always positive, and it only equals 0. Well, I guess say it's positive. It's always non-negative because we don't want to ever have negative distance. But we also want it to only be 0 equals 0 if and only if x equals y. So the only point that is a distance 0 from another point is itself. So you can't have 2 points in your space that are distance 0 apart. There's always some positive distance between any two distinct points. Okay. The second one is what we call symmetric, and that is rho of xy needs to equal rho of yx. And this just means that the distance from x to y is the same as the distance from y to x. So no matter which direction you travel, you're always getting the same distances. And then finally, the third one is the triangle inequality. And so that is rho of xz should be less than or equal to rho of xy plus rho of yz. So the book used a slightly different, they switched the letters around, but it's the same idea. So this is the triangle inequality. And we can see why the triangle inequality should be true. And that is, if you've got x, y, and z, then the distance directly from x to z should be less than the distance if you went to y first. And at worst, they should end up being the same distance whenever you have x and z and y is like somewhere on the distance, then it's the same as taking the two distances between. So if y is right in the way, then you go through y on the way to z and the two distances add. But if y is out of the way, then it's further to go through y than it is to go directly to z. So this is the triangle inequality. So these are the three basic properties of metric spaces. And let's spend just a little bit of time thinking about some common metrics that are out there. So the first one is what we call the usual metric. So if you see someone say the usual metric or the Euclidean metric, then what they mean is this. Well, if it's R, then they mean the metric rho of xy is just the absolute value of x minus y. So this is a really natural way of measuring distance. And this is the one we've used so far this semester. And we know that this has all the properties that we expect. So it's only equal to 0 when they're equal. It's always positive. It does x times y, x minus y, y minus x are the same number, and the triangle inequality holds. R squared in the usual metric or the Euclidean metric is the square root of x squared. Hold on, it's the square root of x1 minus x2 squared plus y1 minus y2 squared, where this x is x1, y1, and this is x2, y2. Maybe we should call this x. Maybe these are not very good names, but in a sense, we know this. This is the distance formula in R2. And in higher dimensions, we have the exact same properties being true. Okay, and this also fits the metric. So often people will, we'll use little bars to represent these, and a common notation, the one the book likes, is to use double bars. And so this is kind of the magnitude notation that you might remember from vectors. And so if you remember vectors, this is how you measure the magnitude of a vector. So this is the usual metric or the Euclidean metric. And so this is what we do most often. But there's no reason we have to do the normal thing. So let's start off with one thing that might be rather unusual, and that is what if we do something called the discrete metric. The discrete metric on any space x, but we could do this for the real numbers, is as follows. Rho of xy is going to equal 0 if x equals y, and it's going to be equal 1 if x does not equal y. And notice this discrete metric actually works for anything you could possibly imagine. So x could be the set of all people on Earth, and then the distance from one person to another is 0 if it's themselves, and 1 if it's anyone else. So that's one way you could measure. That's one way you could measure distance in the discrete metric. And this is really unusual, but notice obviously it fits the first property, because obviously rho of xy is always greater than or equal to 0, and rho of xx equals 0, and it doesn't equal 0 if it's not equal to 1. So the first property is pretty automatic, and the second property is also pretty automatic. So really the only property that's worth thinking about is the triangle inequality. And let's ask ourselves if the triangle inequality is true. Well, the first thing we might ask is we go, well, what about rho of xz? And ask about that, and you go, well, there are two things. Well, so rho x and z could be the same number. So we want to prove this is less than or equal to rho of xy plus rho of yz. And so case 1 would be that x is equal to z. Then you just get 0 is less than or equal to rho of xy plus rho of yz. And that's obviously true. If y is equal to x and y, then 0 is less than or equal to 0 plus 0, and you're good. And if y is not equal, then 0 is less than 1 plus 1, which is good. A second case might be the case where x is not equal to z. And then we have to ask, well, is y equal to one of the others? Then we might say, if y is equal to, say, x, then we get 0 is less than or equal to 1 plus 0, because y plus, wait, what am I doing here? 1 is equal to 1 plus 0, because x and z are different. I'm still, sorry, I'm saying this all. Well, let's actually write the thing out so I don't mess up one more time. Rho of xz is less than or equal to rho of xy plus rho of yz. Well, this one's obviously not 0. This one's obviously 1 because x is not equal to y. This is 0 because x is equal to y. 1 because x is not equal to z. And then finally, if x is equal to y, then y is also not equal to z. So this is 1. And so that one works. Whew, sorry about all those misspeaks. Okay. So finally, we could do case 2 or case 2 part 3. Case 3, we could let x not equal z and y not equal x or z. So y is not equal to any of them. If y is equal to z, you can see that the problem is analogous to what we just did. And if that's the case, then what do you get? Well, you get 1 is less than or equal to 1 plus 1, which also works. So the discrete metric is obviously a metric. It feels a little strange, but it is a metric. Okay, let's go through just a handful more. So there's one that I call like the driving distance, the distance metric. And that is, we'll let x be the set of all cities in, say, cities in North America or something like that. Cities that you could drive to in North America. And then what we'll define is we'll define rho of any two cities to be the distance when driving between the two cities. And we're going to disregard things like off-ramps and stuff, because I guess technically maybe going from one city might be just a few feet shorter than coming back because of off-ramps. But we're just going to say, we're going to take like the general heart of the things. And what you can see is that this has got to be a metric, because the distance is only 0 if the city is the city itself. We probably have to be a little bit more clear about what this distance is. Maybe you're going from like the heart of the city or something. But the distance is only 0 if you're staying in one spot. And then the distance we're going from, say LA to San Francisco is the same as the distance maybe going backwards from San Francisco back to LA. And then so the distance is symmetric. Then furthermore, if you're going to go to New York City, it's quicker to go straight from LA to New York City than to go through San Francisco first. So obviously, because you could just go to San Francisco, and that's one way to get to New York City. And so if there's any other method, then you're going to get there a little bit faster. But what's interesting is this is a metric, but notice there's no logical way to like add or multiply things in here. So this set has no addition or multiplication or division or anything like that. It doesn't even have any size, so it's not like some numbers in the set are bigger than other numbers. What do you get when you add LA to San Francisco? It doesn't make sense. I don't know, maybe it's the start of some joke. So if you've got a good, what do you get when you add LA to San Francisco joke, let me know. Okay, so that's a metric that we can talk about. And then finally, we have a couple that are simpler. So one common one is if say S is a subset of X, then S is also a metric using the same row of XY metric that you used in X. So this is what we'll say is it's the inherited metric that you inherit from the larger subspace. And this is this is a common thing. So one example might be to say the rational numbers with metric x minus with the absolute value metric that we use for the real numbers. So this is a metric in a metric space. So once you have one metric space, any subset of it is also a metric space. Okay. I feel like that was a little dramatic, but let's keep going. Now, once we talk a little bit about metric spaces, we're ready to talk about open and closed sets. So we kind of talked about open and closed sets last time, and what we decided is an open set is something like this. An open set means that if you take any x value in it, then you can put another open set around it. And so because of this, we need an equivalent language, and I kind of introduced this last time, but one thing is called a ball. And so a ball is this idea right here. Some people call them neighborhoods. So sometimes you call it a neighborhood is this little part right around X. You'll say there exists a neighborhood or there exists a ball. So what is an open ball? Well, an open ball, we'll use the notation B with a little r of X. So this is the open ball centered at X and radius r. Then that ball is just the set of all y in X such that rho of xy is less than r. And then we get the closed ball is the exact same thing, and it is just the set of all y in X such that rho of xy is less than or equal to r. And so, there's our ideas of an open and a closed ball. And the open ball has the notation, and sometimes people will use this, which we'll talk about in just a couple of videos. Sometimes people will put a bar over it to denote the closed ball, and you'll kind of see why we might use that notation in just a little bit. Okay, so these are the open and closed balls. So once we know what an open and closed ball is, we can define an open and closed set as follows. So an open set S is open if for every x in S there exists, say, an epsilon greater than 0, such that the ball of radius epsilon around X is still in S. And so what does this picture look like? This picture looks like we have some set S. Maybe I should, let's draw it with dotted lines to kind of demonstrate that's what's going on. And then you take some X value in here, and then you can make a ball around it that's still inside of your set. So that's what it means to be an open set. Notice if I had drawn, say, a closed set instead, say a set that looks like this, then I could have picked that point right on the edge, and it doesn't matter how small my ball gets, I always have points that are outside the ball itself. Okay, so what is a closed set? A closed set S just means that the complement is open. Okay, that's not a very satisfying definition, but that's what it makes. It makes fewer definitions to worry about. We just say S is open, and then if the complement is open, then we say it's closed. Okay, so let's just go through a couple quick open and closed sets. So, for example, the ball of radius r about X is open. So why should that be? Well, if I take the ball of radius r about X, well, let's pick some point inside that. Let's call that point, how about that point A? So I'll let A be an element of the ball of radius r about X. And then I can make an open set around A because I know that A has some distance to, X. So I will let let's just say, we'll let D be the distance between X and A. And then all I have to notice as well, what is this distance? I just need something shorter than that distance right here. And then I'll let epsilon be r minus d. And if I wanted, I could let it be r minus d divided by 2 or something. But then the ball of radius epsilon around A must be an element of the ball of radius r about X. How do we prove this? Well, the way you do it is you go, well, pick some point in that set So let's pick some point inside of that set and show that it has to be, so pick some point, say B. And then what I know is that, what is the distance? So let B be in that smaller ball. And then how do I know B is also within the larger ball? Well, I know that the distance from B to X is less than or equal to the distance from B to A plus the distance from A to X, but this number is less than or equal to R minus D plus D plus R, sorry, R minus D plus R minus D plus, hold on, what am I doing here? X to B is less than X to A, which is, yeah, so R minus D plus D, which is equal to R. So this distance must be less than or equal to R, so that means B must be inside of my bigger set. Okay, this may have felt a little bit like gibberish, but what we're really just saying is that an open ball must be open, because if you take any small point within it, you can make a smaller ball within that ball that still fits. Okay, so that's what it means to be an open ball. Similarly, I could show that a closed ball must be closed, but let's do something more interesting than that. Let's just show that an individual point itself must be closed. So if I have any point in my set, that set must be closed. And so the way I do that is I show that my set itself minus that point is open. And so what I'll do is I'll just pick some element, whatever I want to call it. Let's call it X in X minus A. And then all I'll notice is that there's a distance between X and A. And then let rho of XA equal D, and that must be a positive number because X is not equal to A. Then I just simply point out that the ball of radius, say D over 2, around X must be a subset of X minus A. And let's not go through the proof, but if I wanted to, I could prove that. So that could be proved by picking some random point. Let Y be in the ball of radius D about 2 of X. And then I show that the distance between Y and A, well, what I do is I show that Y can't be A, right? That Y must be in X minus A. And so I do that. So I show that Y cannot equal A. And the way you might do that is you might show the distance between Y and B is less than D, and so therefore it can't be equal to A. Okay, so this is how you might go about trying to prove something like that. But that's good. So a single individual point must be closed. An extension of this is that any finite sets must be closed. So finite sets must be closed. And now the interesting one, I gave this to you last time, and you all didn't do it, but I want to talk about it. So the first thing that we notice that R, the set R, is open. And this is just pretty simple because you let X be a real number. Tell you what, let's not say R. The set X itself must be open. So let X be an X and R any real number. Then the ball of radius R about X must be a subset of X. So X is open. Okay. Similarly, the empty set must also be open. Oh, I drew my empty set backwards. What am I thinking here? The empty set must be open. Why is that? Well, our theorem looks like this. It says if X is in X, then there exists an epsilon in R such that the ball about epsilon of X is a subset of our set. Oh, maybe I should have, instead of X, maybe I should have done E. So this is what it means for a set E to be open. Well, notice this first half of my if-then statement is always false. And what you remember from your intro to proof class is that if the hypothesis is false, then that means the if-then statement must be true. And so this is open, and this is what we call a vacuously true statement. Okay, well, this is actually really interesting because this means that the empty set is open and X is open. But what is X complement? But then notice X complement is the empty set. And so X complement is also open. And then what is the empty set complement? It is X. And so it is also open. But that means that X is closed. And that means the empty set is also closed. So the empty set and X are both closed and open. So there exist sets of all four types. So sets, as I said, sets are not like doors. Sets can be open, they can be closed, they can be neither, or they can even be both open and closed. And some people like to call those clopen sets. I'll let you decide if you think that's a phrase worth keeping in your vocabulary. All right, once we've defined open and closed sets, we've now found a way of talking about distance. And now that we have a way of talking about distance, we can talk about convergence. And so we can take our old definition that said xn converges to x if for all epsilon greater than 0, there exists a capital N such that n greater than capital N meant that the distance between x and xn and x was less than epsilon. So what we can do is we can take this definition and just erase that distance and replace it with a more generic idea of distance. And we have our definition for what convergence means inside a metric space. So here's our metric space convergence. Now, similarly, we can do the Cauchy definition. And what would the Cauchy definition look like? Well, let's not write it down. I'll let you go through all the first part, but then we'll have rho of xn and xm less than epsilon. So instead of having absolute value of xn and xm, we'll have this distance metric. The distance between them is less than epsilon. Similarly, we could have the definition of bounded. And we could use all of our bounded definitions that we have earlier, but instead we would say something like there exists an M such that rho of x and y is less than M for all. Maybe for bounded we might need like some target point that we're comparing everything to. So we might say a sequence is bounded if there's some. This one might be a little bit more complicated. Maybe we need to let x be some element in our set x, and then there exists an M such that x and xn is less than M. Because you can only do distance in relation to some other point. So you just pick some point to show what it's related to. Okay. So there's our ideas, and by the way, we can prove all sorts of things that we proved earlier. So for example, we can prove that if it's convergent, it must be Cauchy, and the way you do that is the same proof earlier, except you replace your absolute values with balls, and then you use the triangle inequality the same way you did in the proof that we did earlier in the semester, and that works out just fine. So I may ask you to do things like that. Convergent sequences are bounded. You do that the exact same way we proved things earlier in the semester. Subsequences are converge. Sequences have only one limit. So there's all these things that kind of come natural once you do these things. There are a couple ways of kind of thinking about convergence in open and closed sets. And one way of it is thinking about this. So suppose xn converges to some x in an open set E. So what that means is that I have some open set here, E, and then I have some point x inside of it, and then I have my sequence xn converging to those e's. Well, what this means is that so if notice I can actually redefine my definition. This means if there exists some capital N in the some capital N such that for all n greater than capital N, well, notice I could redefine things just a little bit, because what I would like to say is ball of radius epsilon around not the ball, I would say that xn rho of xn and x is less than epsilon. But notice what this is really saying is that the ball of radius epsilon about x is contained in my set E. So notice that if I make my ball small enough, I get a ball around here that's always inside my E. But what I'm really saying is that if I have convergence, then that means at some point, that was a mistake. Then that means at some point along my set, I reach a point where every point in my sequence must still be in E. So I can't have a bunch of points that aren't in E converging to something that is in E. So what I would like to say is that there exists an N such that for all n greater than n, xn is an element of our capital set E. So that's exactly what convergence means, and notice this comes exactly from the way we defined our definition earlier. So let me just say that one more time, just because I can sometimes say things in a bit of a clumsy way, so I'm sorry about that. That's the nature of teaching higher math. So suppose I've got my set converging to something like this. So here, I'll let these be my x values, and these will be my xn values converging. And what I know is I know that because this thing is an open set, that there must be some ball of radius epsilon that's contained completely inside of E. But then what do I know? Then I know there must be some point, capital N, in my sequence such that every n is the distance of every n is less than epsilon. So therefore, each of those x little n values, all of those x little n values have to be in that ball of radius epsilon, but that means they have to be in E itself, because the ball of radius epsilon is contained in E. Okay, so open sets have this really nice result, right? And that is that once you have something converging to something in an open set, then you can know that you can cut off that sequence at some point, and every point after that in the sequence must be in that open set. Okay, closed sets have kind of a converse to this, which is an interesting result. And that is that a closed set has this. So maybe E is closed if and only if every sequence xn contained in E, let's say every convergent sequence made up of elements in E has xn approaching to some x which is still in E. So in other words, the limit value is still in the set. Okay, so if it's closed, then the limit value must still be in the set. Okay, so how am I going to prove this? Let's just sketch out two proofs for this really quick. And by the way, these are the types of proofs that I hope you all are able to do at the end of this section. So I hope that these proofs don't appear too impossible or too daunting. Okay, so let's start by this part of my implication. So let's have closed implies that x is an element of E. And let's just sketch out the idea of the proof. So what we're going to do, we're going to let xn be some set in, let the xn's be in E, and x be an element of E complement. But then what do you know? From the last theorem, there exists some capital N such that for all n greater than capital N, xn must be in E complement because E complement is a closed set. But then this obviously directly contradicts the fact that all of the xn's are in E, right? So then I have xn in E and E complement at the same time. So that's impossible. So we see that couldn't have happened. Okay, so if it's closed, you see it must be in E, because otherwise, if X is converging some outside of E, the outside is an open set, and you can make some ball around that and find points in my sequence that are not in my closed set anymore. Okay, so let's turn it around and go the opposite direction. So let's say, what if I wanted to show that convergent sets are closed, but let's actually do the opposite by assuming that E is not closed, and show that E being not closed means that there exists some sort of X such that Xn is in E and Xn converges to some X not in E. So I'm going to show that if it's closed, then every convergent sequence must happen, and if it's not closed, then there exist convergent sequences that don't happen. So in that way, then we know that these two statements must be the same statement. Okay. So what I'm going to do is, the way I'm going to prove that is, well, since E is closed, E complement is not open. And so if E complement is not open, then that means there must exist some X in E complement such that for all R, the ball of radius R about X is not a subset of E complement. And so what I will do is I will now create a sequence. Create a sequence Xn as follows. Create a sequence Xn as follows. Create a sequence as Xn as follows. Well, the ball of radius 1 over n about X is not a subset of E complement, so there exists a point. We'll call it X, let's put a little prime on it, X prime in E, and X prime is in that ball of radius 1 over n about X, and then I will just call X in that X prime. And there could be many of them, you just have to pick one of them. And then what do I notice? I now notice that those Xn's right there, and I'll come right here. Then those Xn's, sorry about that, my dog went crazy. Okay, then those Xn's obviously have to converge to our X, which is in E complement. Okay. Well, great. We have just a couple more things. So there are a couple unexpected results that show up from convergence. So we see, by the way, before I go on, let me just say that this theorem right here that we had, this theorem is a second way of defining what it means to be closed. So one way of saying what it means to be closed is that E complement is open. Another way is to define closed in terms of every convergent sequence. And these two are equivalent. Yesterday I was kind of hemming and hawing about this in class, so sorry if that was a little confusing. But what's essential is that they're actually the same. So you can choose the one you want to use. So if there's a proof that says prove blank is closed, one way to do it is to look at the complement and show it's open and find open sets. Another way to do it is to talk about sequences in that set and show that they all have to converge. So these are two equivalent ways of talking about convergence. Okay, so finally, there's a couple interesting, surprising results from convergence. The first is, I want you to notice something about the discrete metric. Well, notice the discrete metric means that rho of xy is less than or equal to 1 for all x and y in a discrete metric. So what does that mean? Well, that means that any sequence in with the discrete metric is bounded. It's bounded by 1. So I could give you an example. So for example, if we're doing R with the discrete metric, then I see that this set K is bounded. But it is bounded, but it has no convergent subsequence. And we saw that that wasn't possible earlier. But we saw earlier in the semester that every bounded sequence has to have a convergent subsequence. Well, that's true as long as we're dealing with the real numbers in the usual metric. This is not true for every metric. So here's a metric in which the Bolzano-Weierstrass theorem is false. So we will actually say we will actually call this its own property, and we'll call it the Bolzano-Weierstrass property, is the property of metrics that every bounded sequence has a convergent subsequence. So there'll be times when you have a theorem and you'll say, let X be a metric space that has the Bolzano-Weierstrass property. Notice we have to say that because it's not guaranteed that every metric space has the Bolzano-Weierstrass property. Okay. The second thing I want you to notice is that Q, if we think about the rational numbers, the rational numbers can be defined in interesting ways. So let's talk about the rational numbers with the usual metric with the sequence as follows, with the following sequence. And we'll let x0 equal 3, x1 equal 3.1, x2 equal 3. I can't write 3's right now. Look at that. 3.14, x3, 3.141, x4, I'm going to stop, 3.1415, etc. And what I'm going to do is that xn is the first in digits of pi. And then what I notice? Well, I notice that each xn is a rational number, and the xn's we would like to say they converge to pi, but we can't say this. This is not something we're allowed to say because pi is not in our space. This is not true since pi is not a rational number. When we talk about convergence, we can only talk about convergence within whatever metric space we're talking about. So inside Q, this sequence does not converge. So here we have a sequence that looks like it should converge but doesn't converge. But again, what do we mean by the looks like it should converge? Well, what I really mean is that this sequence is Cauchy but not convergent. But not convergent. And again, we saw that for the real numbers, this was impossible, that every Cauchy sequence was convergent. And so we will call sequences that where every Cauchy sequence converges, we will call those complete. And if you remember, that was the property of the real numbers that we kind of used to define what the real numbers are. So a sequence is complete if every Cauchy sequence converges, but notice that it's not true in general. The complete is something you actually have to put into your theorem if you want this to be the case. All right. Well, that takes us to the end of our video, and I'll have another one coming up in just a little bit as we explore metric spaces and particularly this idea of convergence a little